So now we're looking at the second half of chapter 8, which is the factoring unit. Factoring is dividing, or it's kind of a reverse distribution. So what we've been doing is using the distributive property this way to get this answer. Well, now we'll be given the answer, and we have to factor it into a monomial times a binomial, or we'll also look at factoring it into a binomial times a binomial. So the first type of factoring we're going to be looking at is GCF, or greatest common factor. And you've seen this with two numbers, like my first example. If we're looking for the greatest common factor of 15 and 27, you would think about what goes into both numbers. If they're not numbers you're familiar with, you can do your factor tree. So 15 is 3 times 5. And you'll stop your factor tree when you have all primes. So for 27, I might factor that into 3 times 9. 9 is not prime, so I would keep factoring that. When you've got your factor tree, you look at both trees and find any numbers that are in both. So I've got 1, 3 in both trees, in each tree, so the greatest common factor would be 3. Thinking about variables, you can do it the same way. Remember, x to the 5th means x times x times x times x times x. X squared means x times x. So looking at our factors, how many x's do we have in both? It's not exactly a factor tree, but in both factors. And I've got x times x in both cases. So the greatest common factor would be x squared. Hopefully you see the shortcut with variables is you just look for the smaller of the two exponents, because x times x can go into x to the 5th power. All right, so first we're going to take a look at just finding the greatest common factor. So looking at our terms 6w cubed and 14w. I might start by looking at just the numbers and ignoring the variables initially. 6 would be 2 times 3. 14 is 2 times 7, so the GCF for my numbers would be 2. And looking at the lower of the two exponents on my variable, I've got w cubed, which is w times w times w, and w, so I have 1w that would go into each term. And that's the smaller of my two exponents as well. Second example, I need to find the GCF for 60 and 45. Again, if this isn't one that you just know off the top of your head, start taking a look at the factor tree. And you can use any two numbers that you know multiply to 60. Probably most of you might initially think 6 times 10, so we can take a look at those two. And then 6 is 2 times 3, and 10 is 2 times 5. So again, you stop once you've got all prime numbers. 45 you might recognize as 5 times 9, and 9 is 3 times 3. So looking at what is in both trees, I see a 3 and I see a 5. So what you do is you multiply those together, not all 4 of them, just the numbers from one tree. So we've got 3 times 5, or 15, for the GCF of 60 and 45. And since our 60 has a y and our 45 does not, y does not go into both terms, so our GCF is just 15. So for C, I'm going to look at negative 18 and negative 6, and I see a negative 6 for my GCF. A negative 1 can be a common factor as well. And because it's 1, you can actually pull a negative 1 out of a positive number and call that a GCF as well. Looking at my variables, the smaller of the two exponents is 2, so q squared would be my GCF for the variables. So now we're going to take a look at how to factor using GCF. So obviously the first thing we need to do is identify what our GCF is. So looking at 12 and 9, my common factor would be 3, because 3 goes into 12 and 9. And I don't have a variable on both terms, so 3 is my common factor. And then we divide. So think about dividing each term by 3. Factoring is the opposite of distribution, so we're dividing instead of multiplying. 12x divided by 3 gives me 4x. And negative 9 divided by 3 gives me negative 3. With factoring, you can always check your answer. You can distribute and see if you get back what you started with. Plus, in case you don't find the greatest common factor right away, look at the terms that are left, 4x and minus 3. and check to see if they still have a common factor. 4 and 3 do not, and again, there's not a variable on each term. But if we distribute, 3 times 4x gives me 12x, and 3 times negative 3 gives me negative 9. So they are equivalent. Next example, I'm going to look for the GCF of 32 and 8 goes into both of those. Then I'm going to look for the GCF of my variables, and I've got y cubed and y squared. So the smaller of the two powers is the squared. So I'm going to divide each term by 8y squared. 32 divided by 8 is 4. And remember, when we divide powers, we subtract the exponents. So think about this y cubed as y times y times y. And my y squared is y times y. So 2 of them cancel, leaving me with y. Or 3 minus 2 is 1. My second term, 8 divided by 8 is 1. And y squared divided by itself is 1. So we do need that 1 there as a placeholder because we're adding 1. We're not multiplying by 1. So if you were to check this, 8y squared times 4y, 8 times 4 gives me 32. Adding the exponents, we get y cubed. And 8y squared times 1 gives me 8y squared. So we have to have that 1 there as a placeholder. Last example on this page, we've got a negative 20w squared and a positive 16w. So I have two options on this one. With my first term being negative, I would pull out a negative 4 as my GCF as opposed to a positive 4, because inside the binomial I like my first term to be positive. And then the w squared and the w, the smaller of the two exponents, is 1, so we're going to pull out 1w. Dividing negative 20 by negative 4, I get 5. W squared divided by w is w. You can also think about it as, with the variables, I like to think about it as pulling a w out. So I pulled out 1w, and there's 1w left for inside my parentheses. 16 divided by negative 4 is negative 4, and I pulled the 1w out. So there's no variable left on that second term. So double checking, I've got a lot of errors going on here, but the negative 4 times 5 gives me a negative 20. W times w gives me the w squared. And then the negative 4w times negative 4 gives me the positive 16w. This is our last page. This time we're looking at 3 terms instead of 2 terms. So finding the GCF for all 3 terms, so looking at 40, 25, and 80, I'm seeing 5 as my greatest common factor. And all 3 terms have 1a on them. So 5a is my greatest common factor. 40 divided by 5 is 8. I pulled out 1a. I have 2 a's left, or a squared. 25 divided by 5 is 5. I pulled out 1a, which gives me 1a left. And 80 divided by 5 gives me a minus 16. And I pulled the a out, so there's no a's left. Looking at the 3 terms inside my parentheses, 8, 5, and 16 have no common factor, and there's not a variable on every term, so I think I found the greatest common factor. For b, I have no coefficients. I do, but my coefficient is 1. We don't pull out a common factor of 1, so we're just going to look at the variables. And my smallest exponent is 2, so I'm going to pull out an x squared. I had 6 x's on my first term. I pulled 2 of them out. That leaves me with 4, or x to the 4th. My second term, I pulled out 2 x's, leaving me with 2. And my third term, remember, this is where you might want to think about the dividing again. I'm dividing by x squared. If you started with 3 terms, you have to have 3 terms inside your parentheses. So common mistake is students losing that 1 as a placeholder. It's a plus 1, not a times 1, so we do have to write it. And you can always check your answer by distributing back. If you had stopped here and you distributed back, you'd get x to the 6th minus x to the 4th, but you would be missing that x squared piece. So that's why we have to have that 1 there to get that x squared term on the end. Last example, looking at 9, 27, and 63, I see a common factor of 9. Looking at my variables, I see the smallest exponent is 3. 9 divided by 9 is 1, so I don't need to write that because I'm multiplying by m to the 4th, which is what I have left when I pull 3 m's out of 7 m's. 27 divided by 9 is 3. I pulled 3 m's out, which leaves me with 1. And 63 divided by 9 is 7, and I pulled all 3 m's out.